Okay, so this video overviews the second of the two main analysis techniques that we will go through in this course. Specifically, this one is called mesh analysis, where mesh analysis uses only Kvl equations to solve for circuit parameters. Just like nodal analysis uses only KCL equations. Okay, so we're going to use only voltage law equations. That's the sum of voltages around any closed loop equals 0. But we're not going to do it over any closed loop. We're going to do it over what we call meshes. So meshes are circuit loops that do not enclose any other loops. So they can be thought of as the minimum set of loops in a problem. So for example, in this problem we have, while we have 6 closed paths, if I label each subloop as 1, 2, and 3, we've got loop 1, loop 2, loop 3, loop 1, 2, loop 2, 3, and loop 1, 2, 3. So we have 6 possible closed loops. KVL works for all of them. But in mesh analysis, we're only going to be doing KVLs on loops 1, 2, and 3 in order to solve the problem. Okay, so I'm going to demonstrate mesh analysis by example. So in this problem, we've got, based on the last description of meshes, we have 3 meshes. We'll call it mesh A, B, and C. And we are going to analyze the circuit via mesh analysis. So the objective of this problem is going to be determine the currents I1 through I4. Okay, so the first thing that you do in any mesh analysis is define what we call mesh currents. So note that the currents I1, I2, I3, and I4 are what we call branch currents. This is what we've been dealing with so far. I1 is the current through the 1 ohm resistor and subsequently through the 10 volt source. I2 is the current through the 5 ohm resistor. I3 is the current through the 2 ohm resistor. And I4 is the current through the 10 ohm resistor. So what I mean by mesh currents are that they are the currents that are just mathematical constructs helpful in solving the circuit. They're not physical currents. So we think of these as single loop currents. In other words, the relative current in each loop, in each mesh rather, A, B, and C. So for example, in mesh A, I might define mesh current I sub A. In B, I'll define mesh current I sub B, and I can pick any arbitrary direction. I just tend to pick clockwise, and mesh current IC. So IA, IB, and IC are what we call the mesh currents. So again, we kind of think of these as the relative current in the loop. It's not that these currents are necessarily the physical currents. It's that IA is kind of the contribution of the total current due to this loop, likewise for IB and IC. But we need to relate these mesh currents, these mathematical constructs, to the physical branch currents that we have in the problem. So we can do so as follows. So looking at branch current I1, we note that I1 is going right to left through the 1 ohm resistor and the 10 volt source, but IA is going the opposite direction. Note that IA is the only thing going through the 1 ohm like I1. So I1 can be rewritten as negative IA. They're going in opposite directions, and there's only one mesh current going through that 10 volt source and 1 ohm resistor. I2 is the branch current through the 5 ohm resistor. We can split I2 into 2 mesh currents. There's IA going through the 5 ohm resistor in the same direction. So I2 is going to be positive IA, but IB is going the opposite direction, also through the 5 ohm resistor, so we subtract off IB. In other words, the physical current I2 can be split into two terms due to mesh A and mesh B, and those are IA and IB. And they're going in opposite directions through the 5 ohm resistor, summed together to give us the actual current I2. Okay, using the same logic, I3 is going to be equal to negative IB. IB is the only mesh current going through the 2 ohm resistor, and it is defined in the opposite direction of I3. I4 is the branch current through the 10 ohm resistor. There are two mesh currents that make up I4. IB is going in the same direction, so plus IB, and IC is in the opposite direction, minus IC. So now we have taken the four unknowns, I1 through I4, and rewritten them, re-expressed them in terms of three unknowns, IA, IB, and IC. This works because we know that these four currents, although we've written them as four unknowns, they're not independent of one another. They are all related to one another by how these elements are connected to each other. Note that I1, I2, and I3 are related because they meet at a juncture between the 1, 2, and 5 ohm resistors. I3 and I4 and this 2 amp source are related to one another in the same way. Therefore, all currents can be expressed as being related to one another, and we can do so by separating out the contributions of each loop, IA, IB, and IC. Now there's one thing that additional item that we know about this circuit is that if we look at this last loop, mesh C, we have a current source here. This current source dictates the response in this loop. And again, considering this as just a single element that's not joined by any other meshes, IC is the only mesh current that comprises of this branch current. That is 2 amps. So we can actually rewrite the 2 amp source as being made up of single mesh current IC that is in the opposite direction as defined as the source. So we know that IC is going to be equal to negative 2 amps. So in fact, we only do not know IA and IB. So we've re-expressed I1, I2, I3, and I4 in terms of two unknowns, IA and IB. Okay, so after we've defined the mesh currents, IA, IB, and IC, we are going to write KVL expressions. So these are Kirchhoff's voltage law expressions, the sum of the voltages around the loops, and we do so for each mesh. However, we're going to do so in terms of the mesh currents that we've defined, not the voltages across each element. So KVL for mesh A, again, my convention, and you don't have to use this one necessarily, is I'm going to go firstly with the direction of the current that I defined, IA. You go ahead and ignore at this point the branch currents. They're irrelevant because we've already figured out how to relate IA to I1, I2, and I3, and I4, for example. Let's see. So we're going to go with the current direction of IA. So I'll start here at the bottom left, and I traverse through the 10-volt source. If I go from the negative to the positive, I'm calling that a voltage rise, and I'm going to give that a sign positive, so positive 10 volts. Then moving across the 1 ohm resistor, given this direction from left to right as defined by IA, I'm implying the positive polarities on the left, negative polarities on the right, therefore it's a voltage drop. So voltage drop across the 1 ohm resistor is given as 1 ohms minus or times current IA. Note that if I use this convention, all passive elements will be expressed as a voltage drop and will have a sign that is negative. Active elements can have a sign that's positive or negative. I like to use this because it's easy for me to kind of debug if I have an error. I always see a negative in front of the passive element. If it's a resistor, the first term I like to write is the resistance. The second term is the summation of the currents, the mesh currents through it, in this case only IA. Moving on, the next element we see is 5 ohm resistor. Again, it's a voltage drop. It's going to be a voltage drop across a 5 ohm resistor. I'm working with first current IA is going the top down, so I'm applying positive to negative polarity, but IB is also going through the 5 ohm resistor in the opposite direction, so I have to subtract off IB. In other words, the total voltage drop across the 5 ohm resistor is given as 5 ohms times IA minus IB. And then that expression is going to be equal to 0. So note that this is slightly different than what you would do if you expressed it in terms of I1 and I2, where IA is minus I1 and I2 is given as actually IA minus IB. So we've rewritten those unknowns I1 and I2 in terms of IA and IB. When we do this for each loop, we'll find that we reduce the number of unknowns in our system. Okay, so the KVL at loop B. First I go through the 5 ohm resistor, so it's a voltage drop, minus 5 ohms times, now I'm working with current IB, so I'm assuming positive polarity on the bottom, negative on the top, so it's going to be expressed as current IB minus IA in the opposite direction, minus 2 ohms times the only current through that one is IB, and then minus 10 ohms times the current to give me the voltage drop, and that would be IB minus IC in the opposite direction. And that's the third element in that loop. For C, the KVL is not needed because the mesh current is already known as IC equals negative 2 amps. If we were to do this, what it would look like is we have to identify an unknown, and that unknown would be the voltage across the 2 amp source. So we could define voltage Vx, for example, across the 2 amp source, writing a KVL that was minus 10 ohms times IC minus IB, and traversing through, so it's a voltage drop across the 10, positive, negative, through across the 2 amp source is a voltage drop, so minus Vx, and that would equal 0. So if we wanted to find that voltage across that source, that's how we would do so. Okay, so looking back at our system, we have two equations, KVL-A and KVL-B, two unknowns, IA and IB. That's because IC is known. Therefore, we can solve this system. The solution, when we plug that into our favorite solver, like MATLAB, will be IA equals 909.1 milliamps, and IB is negative 909.1 milliamps, and of course IC is negative 2 amps. From this, we can sub back into our relationships to the branch currents and get that I1 is negative 909.1 milliamps, it's the opposite of IA. I2 is 1.82 amperes. I3, 909.1 milliamps. And I4 is 1.09 amps. I suggest practicing this problem again on your own, and another way you can practice this is potentially choosing your mesh currents IA, IB, and IC to be different directions. Okay, you should still get the same solution for the branch currents in the end. If you choose a different direction for IA, clearly the sign for IA will change, but the branch currents that have been defined for us in the beginning of the problem will not be any different.